Okay, so here's what we've got for the first unit. So as I said, this is going to be a brief unit. We might be able to, we'll probably, depending on, again, like it sounds like you guys are pretty okay with math. So a lot of this may be stuff that you already know, and we don't need to spend too much time on it. So we'll just kind of see how it goes. But solving linear equations, significant figures or significant digits in rounding, scientific notation, and metric conversions. Caden, I know that you're in Miami, but we'll be using generally. We use the metric system here in Canada, and so most of the stuff we'll be doing is going to be in the metric system, which is not that crazy. I know that in the States, you guys use pounds and feet and inches. But even space agencies like NASA now use the metric system. So even if you are doing physics in the States, following metric SI units is going to be useful anyway. And there's a few more math skills, so we'll review that, and then and there's a little bit of graphing as well. Okay, so why don't we see if we can tackle a couple of these questions, and that will give me a sense of where you guys are. Can you guys tell me, like, just you can just throw up a thumbs up. Do you guys have the PDF, the course notes on your computers? Do you have them open on yours?
Yeah.
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 Everybody does? Okay, awesome. So I won't bother sharing my screen for this, but I will be referencing what questions I'm talking about, and then I will have like I said, I have this blank Word document that I typically use to do my work, just because it's a little bit easier to use the tools and to do my draw board on here. So you guys can see my screen. It should just be a blank white Word document. And
Yeah.
okay, perfect. All right, so introduction to physics. So let's see how you guys are in terms of just some math stuff. So solving linear equations. Let's just get right into it. Let's try the first one here. Can somebody tell me, first of all, this here, what does it mean to solve a linear, what does it mean to solve an equation to begin with? What is it even asking you for in a question like this, where it says solve?
Asking us to solve, like, get it, the answer.
Get the answer, yeah.
You like put the numbers out of the parentheses and then you just balance out the equal signs and like simplify it.
Yeah, and ultimately in a question like this is we're trying to solve for what is R, right? Or in other words, find R. Yes, we all know the joke. Yeah, found it. But the question is, what is the value of R? So any just let's work through this together. How do we go about solving this type of linear expression or linear equation? Any ideas here? What would you do first?
You multiply like 5 times r plus 1 and then it gives you 5r plus 5.
Yeah, so thank you for that, Ryan. So we call that the distributive property. So what we want to do is we need to kind of remove all the parentheses here so we can collect some like terms. So if you've done this great. If you haven't in a while, there's multiplication going on between the 5 and what's inside these brackets. So if you multiply 5 times r, you're going to get 5r. 5 times +1 gives us +5. on the left side, I do a lot of like 2-for-1, so we might as well do the same thing where we distribute the 2 and the 2r. So 2 multiplied by 2r is going to give us 4r, like that. And then 2 multiplied by -1 gives us -2. And then we still have that +4 remaining. Okay. Any ideas what my next step might be? Remember, we're trying to get r on its own.
Subtracts 4r on both sides.
Right. And why are you doing that, Caden? What's the reason for that?
Because you just want to get like one, like gets, just gets 1r.
Yeah, so in other words, you're trying to collect the like terms. And so in other words, we have this and this are both like terms. And so to move the +4r to the right side of the equation, we're going to subtract 4r. So we're going to be left with -2 plus 4. And then the same thing, I'm going to move this +5 to the left, which means it's going to be -5. And that gives me 5r subtract 4r. If we resolve this, -2 plus 4 subtract 5, what do we get? We've got r on this side. Some basic arithmetic. You can get -3 is equal to r. Okay, so that's basic solving a linear equation. So how are we doing about that? So far, so good? Okay. So just to kind of give you a kind of a heads up is that in physics, we identify relationships between different things and we quantify them using equations. So you'll be seeing a lot of equations in this course. And being able to rearrange an equation either with values or just algebraically is going to be like one of your #1 skills for being successful at physics. So if something like this question here was like, yeah, that was fine, then we're off to a good start. Okay. Let's try something maybe a little bit more challenging. So let's try, because I'm just going to skip a few of these questions, and then your task is going to be to do the other ones on your own. Is like question number 9. Okay, so the other questions 1 through 6 were all fairly similar. So how about this one? Any ideas on how we go about solving this one?
You multiply both sides by 3 and then get y minus 1 equals to 18.
Yeah, exactly. So the idea of rearranging an equation, we're trying to isolate the variable y. And the strategy, you may have called it something different in your math classes. I always say opposite operation. So the operation going on between y minus 1 and this denominator 3 is division. So the opposite of division is multiplication. So multiply both sides by 3 is going to give us y subtract 1 is going to equal 3 times 6, which is 18. And then to isolate y, we're just going to add 1 to both sides. So we're going to have 19. So y equals 18 plus 1. Okay. All right, let's keep going. Let's try with something maybe a little bit trickier. Everybody loves fractions. So why don't we try something like number 13? And I'm going to put this one over here. Over a little bit. So take a look at this guy. And what's our strategy over here?
Multiply everything by 12.
Multiply everything by 12. And why would we do that?
To get rid of the fraction.
It's one way to get rid of the fractions. Yep, we can multiply everything by 12. Any other options? Maybe something that's a little bit simpler. We can do it in a couple steps, but if we're going to go with that one, let's go with that one. So we're going to go multiply everything by 12. So we're going to get 12 multiplying 2x plus 1 over 3. Subtract 12 multiplied x plus 1 over 4 is going to equal 12 times 3 is 36. Great. Now what? How do we simplify this? This is all yours. This is all you're doing, Caden. So now you have to fix this mess.
Cancel the 12 and the 3 and the 12 and the 4.
Yeah, so we can simplify these, right? So 12 and 3. You guys have Black Friday coming up, right?
Yeah.
Yeah.
Yeah, so Black Friday, I always do this in my classes. It's slashy. We got to slash prices, just like Black Friday. So when we start canceling's not, I don't like using canceling. We simplify out. So we're gonna be left with a 4 here. And if we slash these guys, we're gonna be left with a 3 here. So our next line is gonna be 4 multiplied by 2x plus 1 minus 3 multiplied by x plus 1 equals 36. And at this point here, we're kind of back to how we did the first question, right? So distributive property, 4 multiplied by 2x gives us 8x plus 4. This is going to be, don't forget, keep the negative sign, right? So there's going to be negative 3x. Negative 3 multiplied by positive 1 gives us negative 3 equals 36. And then we can start collecting like terms. So we've got 8x over here. Negative 3x is going to give us 5x. 4 subtract 3 is going to be positive 1 equals 36. And I feel like I had a colleague actually come up with these questions. I think number 13. Oh yeah, this is going to work out nicely. 5x is going to equal 35. So therefore x is equal to 7. Okay. So far so good. I'm getting the sense from you guys that this is not giving you too much trouble. Is that fair?
Yeah.
Yeah.
Okay. Awesome. So, in that case, sorry, I'm just gonna, let's move on to something that you may or may not be familiar with. So this is lesson 2 on what we call significant figures or significant digits. And what do we mean by significant digits or significant figures? So I'm going to post this in here. And does the term significant digits or significant figures, is this familiar to anybody? Has any of you guys talked about this in any of your classes before?
No.
No? Okay. So significant figures. All right. So this is where our first thing is. Okay. And I'll add this here. Okay. So all measurements have a degree of uncertainty. Hopefully you can read that. What that means is no matter how precise you are, whether you take a ruler, it's kind of blurry, my background's blurry. When you, as careful as you are, you're always going to have, at some point, you're estimating. At some point, you are not going to be certain about that final measurement in any measured value. And this doesn't matter if it's a tool such as this, or maybe you've got like an electronic balance or a scale where you take an object and you get the mass of it, or even if you're using something as precise as like something that uses lasers. So one of my my parents, one of their best friends, she had a company in Toronto, and her company was basically 3D measurements. And so various manufacturers would need to have a part made, and then they needed quality control. So they would have a part made, a part machined, and they needed a digital measurement of it, right? So think about 3D printing something. Like, let's say you want to 3D print something, you want to copy it. If you don't have precise measurements of it, then you're not going to be able to replicate it. And so she had a machine that basically used lasers, and would scan the whole thing with lasers and give the dimensions of the object with like really high precision. And so even with that, there's a degree of uncertainty. And as we get into the course, we can talk a little bit about things like the Planck length, whatever. But significant digits are how we represent our certainty of measurements. And in science, it's super important to be honest about how certain you are about a measurement. So if you measure something and you are doing the best you can, there's still going to be some uncertainty. And so you cannot claim to have a more precise answer than you really do. And so that's where significant digits come into play. And so we use it to guide us, especially when we're solving a problem, what our final answer would be. So if you're solving a question that has to do with, for example, motion, and you do some calculations, maybe on your calculator, and you say like, okay, here's my answer. Now, what do I round off my answer to? And that's where significant digits guide us. So the rules are for significant digits, as you can see, it says that a digit is considered significant if they include the following. So all non-zero digits, all embedded zeros, all trailing zeros after decimal, and any trailing zero without a decimal if known to be measured. And so I'll show you a couple of examples of what that is. So we have in our notes a couple of examples, and I will do a little copy pasta here as well. And maybe I'll make it a little bit bigger. So in this case here, determine the number of significant figures in each of the following measurements. And so in the first example, this one will follow the first rule that all non-zero digits are considered significant. So if you have a measurement like this, 527.3 kilograms, this is something that has 4 significant digits or sigdigs, okay? Because each of these values is considered significant, they add certainty and precision to the measurement, and so we would count all of them as being significant values, okay? So that one's pretty easy, pretty straightforward. This one right here is only going to have 3 significant digits, because this 5 are all non-zeros. This is what we call an embedded zero, which means that it's bound between 2 non-zero digits. And then this final 0 here is a trailing 0, but it's not on the decimal side. So this is not considered a significant digit. So we say that trailing zeros sorry, my writing is getting a little bit sloppy, are not significant because they do not add certainty to our measurement. They are merely placeholders. The example that I like to use that I'm just going to put down here is, and I'm going to do this for the benefit of, actually, I don't know, I can't do that with, this is the thing about the imperial system, is that it doesn't do base 10. So the conversion is a little bit wonky. So let's say that I had a measurement of, I took something and I measured it to be 1 kilogram. Okay, here's a brain busting question, guys. How many significant digits do I have in this measurement?
1.
Yeah, there's only one significant digit. But for those of you, like especially Samuel and Ryan know this, and Caden, you probably know this as well, is that in the metric system, everything is multiples of 10, which means that if I wanted to express this in grams, the word kilo means 1,000, which means that this would equal 1,000 grams. And so now the question is, how many significant digits do I have?
I think one.
Think one. Caden, Samuel, what do you guys think?
I think one.
Yeah, if you're thinking one, then you are correct. These zeros in this case are merely placeholders. And the way that we can think about it is that if you use like a really a not very precise scale, and it told you that you have 1 kilogram, not 1.0 kilograms or 1.00, just 1 kilogram, that's not very certain. So you have very low certainty. You only have one significant digit. Merely changing the unit from kilograms to grams does not increase your certainty in any way. So you can't get around the certainty problem by simply changing the unit of measurement. If we did, we could just say like, well, why don't I just go to like something like nanometers and give myself 12 significant digits, because there would be 12 zeros following the number one. So that's why a trailing zero is not considered significant. Now, there is one little loophole, and I'll just be like full disclosure, not every physics course, if you take future physics courses, physics teachers will agree with this. But one way to get around that, if I wanted to write a number that's, let's say like I want to do an example. We have a velocity of 100 kilometers per hour. This is not going to be very useful for us to only have one significant digit, because any math we do, we're going to round to one significant digit, and our answer isn't going to be particularly useful because it's going to be so far away from what the real answer is. So to get around that without using scientific notation, I simply add a decimal to the end, but I don't add a zero after that. It just put a decimal on the end. And this is a way of saying that I have a value here, a measurement, and I want to show you that there's 3 significant digits. And so I do that by putting a decimal there, which then makes these 2 zeros significant. Okay, so this measurement here would have 3 significant digits. Versus this measurement, if you saw it like this, this would only have 1 significant digit. Okay, a little squiggly line here. So far so good. Does that kind of make sense?
Yeah.
Yeah.
Okay. The bottom line is, as you'll see when we start doing some problems, is that there are some rules for rounding and for applying significant digits. And the most important takeaway is that if you have a measurement and it's not super precise, then your answer cannot be super precise. You can't have a measured value that only has like say 3 significant digits, and then you give me an answer that has like 7 significant digits. You are saying that you are more certain of your answer, even though you used a very uncertain measurement. Okay. Okay, let's wrap this up. What do you guys think? How many significant digits here are there in example C? This 403 meters.
3.
We got 3. Agree. And what about this last one here? What do you guys think? It's a bit of a curveball.
5.
Got caught with the curveball. So this one is going to have 2 significant digits. Okay. The reason being is that leading zeros they don't do anything for our certainty. They don't give us more precision or more certainty. It's only going to be on the decimal side, any non-zero value. Now, this is going to be different if this was a 1 or a 2, if you started off with some non-zero value. But if you go back and take a look here, actually, I didn't even include it here. So I'll add this to the note here that leading zeros are, that's not how you put, yeah, are not significant. Okay. Only embedded zeros are. Okay. So that's a bit of a tricky one. Because like I said, the thing that is going to make this measurement more precise would be if you started to add zeros after the 5. So if you had 0.0045 and then another 2 or 3 zeros, now you are being more certain, more precise with your measurement. Leading zeros are not giving us certainty in a measured value. Okay. So what are the, where am I here? Rules for significant digits. I'm going to focus on just one because just for practical reasons. And so I'm going to add this here as the rule. I'm going to put this as, I'm going to type it out. So rules for math operations with significant digits. So the main rule here is, we call it the weakest link rule. You guys know where that comes from? The term weakest link?
It's like a saying in English. I don't know.
Yep. Do you know how it's part of a saying? So there's the rest of the saying. What does it go?
A chain is only as strong as its weakest link.
Exactly. So you could have a chain and that chain could be super strong, but if there's one link that's weak, then the chain fails. And so we use that as an analogy for significant digits. And what this means is that, in other words, when performing operations involving multiplication and or division, we round our answer to the measured value with the fewest significant digits. In other words, if we're doing any kind of calculation where you're multiplying 2 or more numbers, it doesn't matter if 2 of your numbers are super precise, like 20 significant digits. If you are multiplying it against a number that only has 3 significant digits, the 3 significant digits is the weakest link, and so your answer has to be rounded to 3 significant digits. The fact that the other 2 measurements are super precise is irrelevant, because the least precise measurement is going to be the weakest link. And so an example would be like example number 2. You guys are able to do something a little bit more challenging. So I'm going to do a different example. So the example here would be, let's say that I've got this. This is going to be like this. And let's say that this is going to be 12.0. Caden, do you know what that symbol means?
Inches.
Yeah, inches. I'm gonna give some Caden because he's outnumbered here with 3 Canadians. So we're gonna have 12 inches on this side. We're gonna have let's go with 8.00 inches on that side, and then over here we're gonna have 2.00 inches. So my question is, what is the vol? No, that's not the symbol. Capital V. What's the volume of this block? Anybody remember that brain busting formula? How do we find the volume of a rectangular prism?
Length times width times height.
Yeah, so this is going to be, so I'd like you to do a quick calculation and give me your final answer for what is this, what is the volume of this block?
192 inches. 2 cubed.
192 cubic inches.
Yeah.
You guys agree? What about 192.0?
Is this same thing?
Which answer is more precise or has more certainty?
The first one, because you have to round to the fewest significant.
Yeah. So the way we look at it is, if we were to write out our measured values, what we've been given, we have a length. Let's say the length, this doesn't really like match with what you can see here, but let's say it's 12.0. We have the width is 8.00, and we have the height is 2.000 inches. In terms of significant digits, we can see that we have 3 here, 3 here, and 4 here. So the correct answer would be this one, because this one has 4 significant digits in the final answer. So this answer, the second one here, is claiming more certainty than we actually do know. So in other words, when you're solving a problem, and it doesn't matter if it's something as simple as what you can see here for volume, trust me, we're going to be doing questions that are much more complex than this. But at the end of the day, you're going to do your work. You're going to write down your information. You're going to apply whatever equation is applicable, and you're going to do the math. And at the end, you're going to take a look at your final answer, and then you're going to go back and you're going to look at those measured values, and you're going to say, ask yourself, okay, which of these measured values has the fewest significant digits? The fewest significant digits is going to be what you round your final answer to. So 192.0, that might be something that you see on a calculator, but you have to round that to the proper number of significant digits. And in this case, it's going to be 3. Okay, so it seems like not a big deal. Like, who cares if you write down 192 or 192.0? Well, when it comes to being representing what you do, representing your work in science. So like when research is done and that research is then shared with the scientific community, you have to be honest with what you're doing, because other people are going to be trying to replicate what you did. So in science, it's all about being able to reproduce what people do. So if you're doing some research and you're trying to answer a question and you're claiming more certainty than you actually do, while somebody else might be trying to reproduce your work and they're not getting the same value. They're getting like, well, I don't have that same level of certainty. So it's not going to be as credible. Okay. All right, how are we doing so far? So far, so good. We just covered it. Okay, so math review seemed to be okay. Significant digits is new. What I'm going to do, just because, like I said, for the sake of being quick and practical, there is a different rule for if your math operations are involving only addition and subtraction. So I'm posting this here, and I'm going to put this here. So this is in that lesson, and I'm just quickly going to go over this. And what this says here is that when the measurements are only added or subtracted, we don't use the significant digit weakest link rule. We round the final answer to the measured value with the fewest number of decimal places. And so in this case here, if we did this, did a perimeter calculation, which would be only addition and subtraction, we would be rounding to the fewest number of decimal places.